Hello and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 16 in the series on section 3.4, Linear Systems, using matrices. In the last video, we learned one way of using matrices to solve systems of equations. In this video, we're going to focus on using the methodology of an augmented matrix. So if we have n equations and n unknowns, we can encode their coefficients into a square matrix like this. The augmented matrix is what we get when we include a new column that also includes what constants these linear combinations are set equal to. Notice that when we get more unknowns, we usually write them with a subscript instead of using different variable names. That's because we want to be able to extend this process to an arbitrary number of unknowns, and if we constrain ourselves to just using the letters, we might run out. So in general, you'll see things like x sub 1 or x sub 2 instead of seeing x, y, z, etc. Now, here we have taken and encoded the coefficients as well as the constants on the other side of the equal sign into this matrix. This is an example of an underdetermined system because we have more unknowns than we do equations. We only have 3 equations, but we seem to have 4 unknowns. Here's another system of equations, but now already encoded as a matrix. These coefficients will be attached to x1, and if we have a 0, it's simply not going to appear in part of the equation. So for example, having 0 x1s, 0 x2s, and one single x3 actually tells me what x3 is for this system. Likewise, no x2s, no x3s, but a single x1 tells me x1 is equal to 300. Now, using these two constants plugged in for x1 and x3, we could figure out what x2 is pretty easily, but all we're supposed to do here is write the system of equations that goes along with this matrix. We don't really have to solve this next one. Here we have another where we're asked to write this matrix as a system. Provided this is an augmented matrix, we're going to use the variables b and s to encode these coefficients, and this column, final column here, to encode what those linear combinations or sums and differences of constant times variables are set equal to. This is an example of an overdetermined system. It's a system that only has 2 unknowns but 3 equations. Let's actually talk a little bit more about those under and overdetermined systems in 2 and 3 variables. If I have 2 equations in 2 variables, we're basically talking about 2 lines. And there's really only 3 possible options that could happen. We could have lines with different slopes, which would give me a single solution. They intersect at one point. We could have lines with the same slopes. Now, if they are in fact different lines, then these 2 parallel lines never intersect, and so these kinds of systems of equations have no solutions. And correspondingly, if we're actually talking about 2 of the same line, then what satisfies one will satisfy the other, and we might have infinite solutions. Now, let's consider what happens if we add a 3rd line. There's a way for 2 of those outcomes that we could possibly get one solution still. In the special case that goes through the original intersection, we might have one solution, or just intersecting this pair of common overlapping lines with a line of different slope might have one solution. However, in general, if they have different slopes all, we might expect there to be no solution unless they intersect at that one common special point, but it's just as easy that they might not. Also, if the 2 lines started out as parallel, there's no way to add a 3rd line and somehow gain a solution that's common to all 3 of them. Likewise, if we started with 2 lines that intersected and added a line that was parallel to one of those, but not equal to it, we would have no common solution to the 3 lines. Finally, if we had an overlapping set of lines and added another distinct parallel line, this likewise has no common intersection. The only way for us to get infinite solutions is for us to have all 3 lines overlap one another. When we talk about increasing from 2 equations and 2 variables to 2 equations in 3 variables, we're making the extension from 2 dimensions to 3. And instead of talking about linear spaces, we're talking about planar spaces in 3 dimensions. So that's going to take some more effort to visualize, but let's start with just 2 planes. How might 2 planes intersect? Well, there's 2 ways that they could have infinite solutions, either a whole line's worth or a whole plane's worth. But there's no way to intersect and only get one single point if we're talking about 2 planes. You can either have a line's worth of intersections or a plane's worth, but you'll have infinite solutions either way. Now, if they are parallel to each other, but don't intersect all over, then we're going to have no solutions, just like our parallel lines case. If we add a third plane, if the two planes intersected in a line and we add a third plane that's sort of just at a random angle compared to the other ones, we're going to intersect in exactly one place. You can see that by tracing the intersections between each pair of planes and seeing how those lines intersect here. There are a variety of ways to get no solution. The most common ways of getting no solution are to wind up having some kind of parallelity involved, but still having at least one of those planes be distinct from the other. If we had two parallel planes and they were cut by a third, they might not intersect at all. If we had overlapping planes, or maybe three distinct planes and they were all parallel, they wouldn't intersect at all. And we might have them be none of them pairwise parallel to each other, and yet still have no common intersection, creating this little triangular tunnel that I've made here. Likewise, there are a variety of ways to get infinite solutions. We might have them all intersect around the same line, similar to the special case for three lines. We might have coplanarity and then intersection with another non-parallel plane, which would give us an intersection of a line, just like the intersection of two planes would. And likewise, we could have a whole plane's worth of intersections if all three planes were actually just common descriptions of a single plane. So what we can see here is we're getting sort of a wider variety of ways that we might have no solutions, and a wider variety of ways in which we might have an infinite number of solutions than compared with lines. The next question asks us about whether or not the elementary row operations will change the solution set of the associated linear system. Now, the idea is that these operations will not change the set of solutions. Let's discuss what they are. We could scale an equation by taking a row, which represents an equation, like, for example, 3x plus y equals 4, and we might scale it by multiplying the entire equation by some constant. This is the same as multiplying by that constant on both sides, and as you could probably guess, that's not going to affect the solutions for that particular equation. We can switch two rows around or interchange them, and that's because if I'm given a system of equations, this is going to have exactly the same solutions as the system of equations where they're given in the opposite order. Order doesn't really matter here. As a final use of substitution, we're allowed to add a scaled equation to another one. Let's say, for example, I had 3x plus y equals 4 again, and let's make something up like, I don't know, x plus 2y is equal to -1. If I want to, I am allowed to take this equation here and multiply it both sides by a constant. Let's call this one r1 and r2. I can take r1 and add to it r2. Let's say, in fact, r2 times -3. And what we'll do is we will replace our original r1 with that equation. Now, what this would do is this would take 3x plus y, and then it would add to that -3 times x plus 2y. Now, we're also going to want to add -1 times -3 to 4. We're adding both equations to each other entirely, which I'll kind of summarize like this. Notice that 3x plus -3x would be 0x's. And -3 times 2 is -6, plus 1 is -5. And -3 times -1 is 3, plus 4 is 7. And so in this case, we would wind up with a new equation. And if I replace that into my equations for row 1 here, equation 1, I would get -5y equals 7 over x plus 2y equals -1. Now, why should this have the same solutions as before? Precisely because we insisted on doing the same thing on both sides. We took and added to one equation -3 times this quantity. But that's the same as -3 times this quantity since they're equal to each other. So we've done the same thing on this side, the same thing on this side, and such manipulations, just like scaling, don't actually change anything to do with the set of solutions. So let's look at problem 6 here. They're asking about some particular row operation like I just gave an example of. This is our r1, this is our r2, and what if I wanted to do 5 times r1 plus r2 and store it as r2? Well, first we want to calculate what is 5r1. It's 5 times these constants. Okay, there we are. And then if I add that to R2, I get the following: 1, 24, 22. Then we want to replace R2 with that. We want to store that as R2. And so we replace the bottom row with precisely those numbers, and that's it. That's what we want. Here we have an interchange to do. They say switch row 1 and row 5. So that would just look like this, taking the -6, 4 and putting it up on the top row, and taking -2, -7 and putting it on the bottom row. For number 8, we're asked to do a single valid elementary row operation to put a 1 in the first place. And there's a couple ways we could do that, but let's just say I think the easiest one is to multiply that whole top row by -1 itself. That changes the sign of each element in the row, and we get the following matrix. So let's talk about how to put an augmented matrix in row echelon form. Although there's a couple places where we might get stuck in this algorithm, let's say that basically it goes a little like this. First, you want to make the upper left-hand corner into a 1 by scaling. That is going to affect the rest of the things in row 1. Then you want to add multiples of R1. Now that it's a 1, it's easy to see what you'd need to add in order to cancel these other elements of column 1. You just multiply by the negative of whatever they are, and then add row 1 times that constant to row 2, row 3, and so on, all the way down to row n. Now, I just want to point out that I am manipulating every element here, so I don't mean to, imply that these all stay the same, but they're really not important. We're just going to let them come along for the ride. The things that we are focusing on, I want to, identify here. So I'm just going to leave these as, A12, A2n, and so forth, but they will be changing as we do these row operations. So now what we'll have at the end of these two moves, or, each one of these is sort of a move, but after we do these two steps, we're going to have a 1 up top and then zeros all the way down. Now we want to focus on element 2, 2 down the diagonal. We want to scale that in order to make that into a 1. So we multiply the entirety of row 2 by that. And now we add multiples of that to every other row in order to get zeros everywhere else too. This is easily done because we have a 1 right here, and so we just need to multiply by whatever, for example, negative of this A12 is, and then add row 2 times that back to row 1 again. And so on and so forth. We'll zero out everything else other than this one in this column. And we can just keep on doing that until we wind up with 1s down the diagonal and zeros everywhere else. This is what's called reduced row echelon form, or RREF for short. Now, we might get caught up at a couple places when we're doing these if there are infinite or no solutions. But if there's one solution, which is to say an n-tuple of numbers, x, y, z, or x1, y1 up to n, xn, then we will be able to put this in reduced row echelon form completely with a identity matrix here and then some constants in this column. Now there is a command on the calculator that's going to accomplish that. We'll take a look at that in a moment. Let's talk a little bit about what can go wrong. You might wind up with 0 equals 0 as one of your solutions. This is going to be a hallmark of having infinite solutions, provided that this is also not happening above it. Now let's talk about this. This is very different. This is 0 x's, 0 y's, 0 every variable is equal to the constant 1. But that means 0 is equal to 1. That's not true. This is a contradiction. And so we have arrived at a no solutions kind of conclusion here. On the other hand, you might see something that looks similar. You might see 1 on the left-hand side and 0 on the right. This is fine. This is nothing more than saying that one of the variables, in this case xn as I've drawn it, has the value 0 in the solution. That's okay. The problem is if we try to say 0 is equal to 1, that's simply not true. Or 0 equals 0, where that's a tautology, and now the above system is underdetermined, and so might have an infinite number of solutions. Now, although I stand by the algorithm that I gave for putting things in reduced row echelon form, some other versions of the algorithm prefer to go down the diagonal and make this what we call an upper triangular matrix first, where we have zeros underneath, but we've sort of ignored the top numbers. This is fine. But the bottom line is that, if we're eventually going to put it in reduced row echelon form and not just row echelon form, then we really should just be worrying about making this entire first n by n matrix into the identity matrix by whatever means necessary. There's actually a variety of moves we could choose. The one they're looking for here, though, is to start getting rid of this other thing that isn't 0 in this bottom triangle. That's this -3. So if we take and replace row 4 with itself plus 3 times row 3, 3 times row 3 will put a 3 here, and then adding that to this -3, we wind up with 0. That's going to give us the following matrix. The next thing we want to do is get a 1 in this column. They're doing this down the diagonal ones and underneath zeros algorithm first. Again, totally fine. I would have made this one 0 at some point in time, and same with the rest of these, but here we are, just moving down the diagonal. How do you make this into a 1? You just scale it. You just multiply all the entries in row 4 by -1/2. Yes, because this should be -2. And so replacing them with -1/2 will give me a +1 here. Little sign error right there. Okay. So how do we put this matrix here into reduced row echelon form? Well, I'll be honest, you can go through this process of switching around the rows until they're in a good looking order. Switching's always fine. Then we want to add multiples to zero out each one of the columns and keep doing that until we have just the identity matrix here. I've listed the operations that I would use, but I have to stress that there is a button on the calculator for this. We want to edit a 3x4 matrix and then put all of our entries in as they're listed in the problem. Once those are in place, if we go back to the main screen and mention matrix A, it'll pop out the matrix that we're looking at. And we can use this to do a variety of things, namely to put the matrix in reduced row echelon form. So we want to go back now and name our matrix matrix A, and there we have it. So this is a good time saver. If you have a calculator that does matrix manipulations, I would highly suggest learning how to do this operation. So I won't continue to show you how to edit and put the keys into the matrix. I will just say that when we have our matrix encoded, it'll look like this, right? Where we have our coefficients and our entries stored as such. Our command for RREF is actually much closer to the bottom of the list, so it's helpful to go up from there. And then typing that in for B, we can get it in reduced row echelon form quickly. So I'll just remark about how that's going to look here on out. I'm not going to keep typing it into the calculator. I'll just say the commands that I used. Here, I'm doing the same thing for problem 12. We encode the matrix, we do reduced row echelon form, we get the following, and we interpret the results. Right? This is 1x is equal to 4, 1y is equal to 3, 1z is equal to -2. Number 13 gives us a situation where reduced row echelon form returns all zeros in the bottom. Now, this is a situation where we're going to have infinite answers. It's one of those kinds of situations. And that's because we only have 2 equations now that are considered to be, sort of giving us any real information. This bottom one just says 0 equals 0, which is of course true. But the top one says that 1x minus z is equal to 5, and the other one says that 1y minus 3z's is equal to 0. Now, what does this tell us? Well, we could either get z's in terms of the x's and y's, that's fine, or we could get x and y both in terms of z, which is called the parameterized version of this. We sometimes include the statement z is equal to z to indicate that z is the free variable here, but we really need not. That's sort of an extra superfluous kind of statement. Of course, z is equal to itself. That's the reflexive property. So here we have one where we've solved this system and we wind up with something equal to 0, but this is one of those okay situations. This one says that x is equal to -3, y is equal to 0. That's 1y equals 0. That's of course fine. That happens when y is 0. And here we have z is equal to -2. So we get this triplet as our answer. Here we have a really excellent inconsistent system. And the reason I say that is because there's this sort of tempting thing right here on the bottom where we don't have an inconsistency. We have this 0 equals 0 situation. You should really think of it as that doesn't tell us anything new. This one, on the other hand, 0 equals 1, that's not okay. That is a contradiction. That doesn't make sense. And so this alone is enough to deduce that there is no solution to this system of equations. I'll just say, if we want to store this as a fraction, it'll be a lot nicer to read these as fractions rather than decimals, and you can use the standard command on the calculator to do that. So here, if I take the reduced row echelon form of matrix F as I have it stored, we get these decimals. But if I just go to math, store as fraction, it'll give me something that's a bit easier to read. Here is our sort of say nothing line, 0 equals 0. And here is our inconsistent line, 0 variables equals the constant 1. Not possible, so this has no solution. All right, let's do some word problems here. We can see that we're talking about a certain sum of ticket sales where we got a certain amount of money from selling a certain number of tickets, which each had 3 different prices. One for full price, one for seniors, and one for student tickets, which I'm going to call the number of which sold X, Y, and Z respectively. They also told us that there were 7 times as many full price tickets as there were student tickets. So if I take the number of student tickets and I multiply it by 7, I'll get this number of full price tickets sold. So that gives me an equation. If I want to write that equal to some constant, I just minus the x over to the other side or minus the 7z's over, and we get x minus 7z's equal to 0. That gives me a third equation that I can use in my matrix. So here I have the sum of all of the tickets is 419. The sum of the tickets number times their price is equal to my revenue. And then we have this one that x is equal to 7z, which can be rewritten this way and so made to fit into our linear system. So I'm just going to type that whole thing into a matrix, take the reduced row echelon form of that to find the following. That tells us that there were 329 full price tickets, 43 senior tickets, and 47 student tickets. Here we have another problem concerning a basketball game. It gives us the total number of points earned in the game. It gives us the total number of individual baskets in the game. And then it says that there were 24 more 2 points shot than 3 points. So I took the number of 3 points, which I'm calling x, and 24 more than that is the number of 2-point shots, which I'm calling y. Solving for the 24 and putting it on the constant side, that gives us x minus y is equal to negative 24. So that's our 3 different equations, the total number of points, the total number of baskets, and this fact interrelating x and y, the 3-point and 2-point shots. Now what we want to do is put that matrix, put those coefficients into a matrix, take the reduced row echelon form of that matrix, and this will read off our answers. There were 4 3-point shots, 28 2-point shots, and 14 1-point shots. Alrighty, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies, and I'll see you in the next one.